Good morning, students. Today we are going to, continue our classes on artificial neural network, where we are going to cover some interesting as well as important neural networks. We have so far done the Perceptron neural network, and obviously we have covered the linear perceptron, that means the single layer perceptron as well as the multi-layer perceptron, right? So now we are going to check what are the other important neural networks which you may have in your syllabus, which you may expect in the coming semester exams. And obviously, those neural networks are equally important, but not, extensively used like our perceptron model or so. But obviously those are some kind of very important milestone in the evolution of the neural network. So starting with that, if you can see the table in this particular slide, you can see that there are four neural networks in particular, I mean on this particular slide. So what happens that this is the first, the beginning of the neural network, which is the McCulloch and Pitts neuron. So when, I mean, in each case, you can see that, I mean, in almost all the cases, you can see that a particular, neural network is being named by some inventor, by the inventor or the designer, I can say. Uh, that means, I mean, based on that, I mean, the name of that designer or the scientist or the researchers, the neural network is being named. So in case of McCulloch and Pitts neurons, obviously the inventors were McCulloch and Pitts. And in that particular case, usually the neurons are arranged in combination of logic functions. So we all know about the logic functions. It is a Boolean logic function. So automatically, based on that particular, logic functions, combination of logic functions, all the neurons are arranged in this particular neural network. Here you can also experience a particular feature which is a very unique one, and that is the introduction of a threshold. That means we have to set a particular threshold value, and automatically based on that value, now we know, because we have covered perceptron neural network, so now we know that based on that particular threshold value, automatically the output must be determined. Now, coming on further, we have Hebbian network, and automatically this Hebbian model or Hebb model, that is designed by Hebb, and this is based on the particular concept that if two neurons are found to be activated simultaneously, then the strength of the connection, that means the weights, that basically are going to be increased. So increased on which manner, increased on what formula or what expression or what mathematical computation, that we are coming in the further slides. Now, in the year of 1958 to, a duration between this 1958 to 1988, more works are coming on the basis of perceptron, where Frank Rosenblatt, Bloch, Minsky, and Papert, those researchers are found, to implement and to model perceptron, by stage. And in that particular perceptron model, we have already seen that weights on the connection path, that means the path which joins one node to another node, that weights can be adjusted. That also, I mean, we have already, covered. Now coming to the Adaline, this particular neural network, which is the last neural network which we are going to finish in today's class, that is designed by Widra and Hebb. And what happens that whenever you're going through this Adaline neural network, you can see that one particular, learning rule is going to be, followed, which is called delta rule. Can you remember whenever we have covered the perceptron neural network, we have talked about gradient descent algorithm or gradient descent learning. So in that manner, this delta learning or delta rule, or you can say Widra and Hebb rule, because those are the inventors, or you can say least mean square rule, all these rules are basically indicating only one rule, and that particular rule is going to be utilized whenever you are going to train the Adaline network. So in that particular rule, what happens that weights are adjusted to reduce difference between the net input to the output unit and the desired output. That means automatically it sounds a bit like a bit of what I say, that is a feedback network. That means automatically we have some desired output, or we can have some kind of target output, and in some measure, we can calculate what is the the output. I mean the net input, or what is the the value or the result which is basically coming to feed to the output unit. So automatically, if there is any error, if there is no error between the value which is coming to the output unit, and obviously with the desired output or the target output, obviously no further action may be required. But if there is an error, then automatically that error is very negligible, I must say, and that particular error is termed as mean squared error, and that is obtained, and that is going to be noted, and automatically can be corrected as well, because we know that all neural networks are designed to correct all the errors by itself, and or by some teachers or by some supervisor, because if that is those are supervised learning network, then automatically the particular weights are going to be updated and so that errors are minimized, errors are corrected, errors are removed, and automatically we can achieve the desired output or the targeted output. Now for the next class, we have these four neural networks, which we will cover in the next class, which is the self-organizing feature map, Hopfield network, back propagation network, and radial basis function network. So what happens in these four neural networks, then you can see that whenever we will talk about self-organizing feature map, in that particular case, we can see that all the inputs are clustered together. Now, can you remember that clustering, that particular, terminology is associated with unsupervised learning network, right? So basically what happens in that particular way, in that particular way, this clustering is performed. And here you can see that the winner takes all policy is being followed to basically fire a particular output neuron. Now, what is that winner takes all policy? If you can remember, in the first class of the neural network, we have talked about competitive learning. We have talked about in that particular reinforcement and competitive learning, what happens that there is a sense of tournament in competitive learning, and in that particular tournament, the winner neuron is going to be fired. So basically, in case of self-organizing feature map, those particular phenomenon is going to happen. Now, in case of Hopfield network, what happens that in case of Hopfield network, we have some fixed weights. And whenever we have some fixed weights, we have to design a particular neural net, which basically, is going to be utilized as a learning algorithm, as well as it can act as associative memory net. So basically, it is, utilized, or it is used as a particular memory as well. In case of backpropagation network, a very, very popular neural network like Perceptron. So it is basically, one kind of neural network where, multi-layer perceptron is being, you can see, but we cannot term it as perceptron. Why? Because we know that in case of perceptron, we have only feed forward connection. But here what happens that here you can see that this backpropagation network is a kind of recurrent neural network where the multi-layer and also the error which is obtained during the learning or during the training phase of the neural network, those error can be propagated backwards from output units to hidden units. So basically, it is a form of a recurrent neural network, and it is a special case of recurrent neural network, but very popular one, very important one, which is a backpropagation neural network. Last is the radial basis function network. This is something a backpropagation network, but here the activation function is very much defined. That is Gaussian function. So basically what happens that all these neural networks are going to be covered in the further classes. So basically starting with the first one, which is the McCulloch-Pitts neuron, I'm going to start with the first neuron with the next slide. And in the meanwhile, you can give your attendance. And whenever this Zoom session is going to be ended, and I'm going to again, be online. Now, starting with the McCulloch-Pitts neuron model. Now, what happens that here, we are having a kind of McCulloch neurons Pitt model where you can see that all the inputs are coming into the weight matrix, right? Into the weight matrix. And what you can see is here connecting parts, or you can say the synaptic ends, which is coming from the weight neuron, and it is used to provide a kind of output. Then there is a summation or the aggregator neuron, which you can say, or you can say the summation or aggregator node, where you can have a particular output. So basically what happens that this is, as we have already told, that this McCulloch-Pitts neuron model, it is the most early phase neural network. This is the earliest neural network, where this MP neurons are basically, M stands for McCulloch and P stands for Pitts. So all those neurons are connected by directed weighted paths. As we know, this is our feed-forward kind of connection. So what happens that we are very much familiar with this activation function, and we have already told that here in case of McCulloch-Pitts neural model, all these activation functions are the logic functions. So basically any function that can be modeled as a logic function, that can be represented as a logic function, that can be modeled by this particular neuron model. What happens that here, if you can see that these are the input nodes, and suppose this is the weight matrix. So if you closely observe the particular figure, then you can see that all the weights can be +1 or can be -1. That means automatically weights can be either positive. Whenever the weights are positive, then those weights are called excitatory weights. And whenever the weights are less than 0, that means weights are negative. Then what happens that you can say that those weights are inhibitory weights. Fine. So automatically all these weights are associated with the communication links from one neuron to another neuron. So here you can see that there is no such particular training program what we usually follow for any kind of supervised learning algorithm. But here what we can expect, that obviously we know that the activation function is a combination of the logic function. So therefore the activation of neuron is binary. So at any step, the neuron may fire or may not fire, because we know that the binary means only zeros and ones. We can expect only two states. So basically what happens, that means if the neuron may or may not fire, if that is the case, then we also know that this particular neuron model must ensure a kind of threshold, right? So firing of the output neuron is based on that threshold, obviously. So in that case, the activation function, which is the combination of logic function for this particular neural model, that may be either 1, if that particular y in, that means the net input of the net input value which is coming to the output neuron, if that is greater than or equal to theta. That means if we have a kind of threshold, then this particular input value must be greater than or equal to the threshold value. And automatically this particular, activation function, that means the firing of the output neuron is based on this activation function. That means this activation function will return the value of 0 if that input, that net input, is found less than this threshold. That means now if there is a threshold, then automatically this particular mathematical computation must follow. If there is no threshold, this is a simple one, then only we can expect whether this weight are going to be +1 or -1. So what happens that if we have this kind of an output neuron whenever is based on threshold, then automatically we can have either excitatory input or we can have an inhibitory input. So what does this mean? That means inhibitory input. Inhibitory inputs means, that means any non-zero input, that means the weight is less than 0. So any non-zero inhibitory inputs, that means will prevent the neuron from firing, and automatically the neuron fires if the net input to the neuron is greater than the threshold. So automatically, that means obviously if that is greater, that has to be greater than the threshold. That means that neuron must be greater than 0 as well. So that means an excitatory. Fine. So for n inputs, suppose we have n inputs, and for inhibition to be absolute, that means if there we have a kind of inhibitory inputs as well, with along with some excitatory inputs, like we have here. That means we have positive weight values as well as we have negative weight values. That means we have excitatory weights, we will have inhibitory weights as well. So in that particular case, what happens that threshold with activation function should satisfy when the condition is this threshold should be greater than nw minus p. So this n is the n inputs, and this is the w and p are the the weights, for excitatory and the weights for inhibitory, right? And the neuron will fire and produce output if it receives, say, k or more than k excitatory inputs but no inhibitory inputs. That means in that particular case, this kw must be greater than equal to theta, and it will greater than k minus 1 into w. So in this particular case, in McCulloch-Pitts neuron model, what we can see is that means those are the conditions to fire a particular, output neuron. So what happens, that means every time whenever we are going to fire this particular neuron in case of McCulloch-Pitts neuron model, then one thing we must sure that we must have a look on the weights as well. So basically, we must ensure that whether the weights are excitatory or inhibitory, and based on that particular process, based on that particular condition, we can compute the mathematical expression or condition which basically satisfy to fire the output neuron, either this or this. That means in that particular case, no such training algorithm is being followed, but a neuron model is performed. Now, a better model than this particular McCulloch-Pitts model, but a simpler one, which is a popular one as well, which is called Hebbian network or Hebb network, you can call. That all this particular, network is what happens that whenever in that particular network, yes, Ujjwal, tell me.
Sorry, ma'am, it occurred by mistake. Sorry.
Okay, okay. So this is in case of Hebbian network. What happens that whenever we have this kind of arrangements, that means we have one input layers. Here, and automatically, we have some connecting links. That means all the weights are must be associated with all these connecting links, and we have also output layers as well. So what happened, that means Can we, am I audible?
ম্যাম শুনতে পাচ্ছি না।
ম্যাম শুনতে পাওয়া যাচ্ছে না।
Am I audible?
হ্যাঁ এবার পাচ্ছি।
Acha, acha, okay, fine. I'm going to repeat. So in case of Hebbian network, if we look at this particular, neuronal model where we have, input layer, we have an output layer as well, and all the weights, all these are connecting links between these input layers neurons and the output layer neurons, and automatically all those connecting links are associated with weights, and weights can be computed or expressed as wij. Now what happens that whenever we have this kind of weight matrix, so whenever we have this kind of weight matrix, we have a kind of weight vector which is going to increase proportionally. Why? Because whenever we are talking about Hebbian network, we have already mentioned that in case of this Hebbian network, a particular mathematical computation is going to happen whenever we are going to update the weight matrix. That is, every time it is going to compute the product of the input and the learning signal, that means the neuron's output. That means every time this weight vector is being calculated by a product of the inputs and the output neuron, which is also a learning signal. Why it is called learning signal? Why? Because that means depends on this weight vector or weight matrix, this output is going to be defined. So that means one kind of learning algorithm must follow here to to obtain this output layer, or to obtain this output neurons. That is why these neurons are called, it is termed as this is the learned neurons, or we can expect that these learning neurons, or these learned neurons, or the neurons output neurons, are getting by some kind of by some kind of having by some kind of learning signal. That is why here it is being written that in this case this is a kind of product of the input and the learning signal, means neurons output. So in that particular case, this weight vector, you can find that it is going to be increased proportionally. That means every time whenever you will move further, iteration by iteration, you will get a particular weight vector which is in increased fashion, and that increment must be followed proportionally, and obviously that proportional to the product of the input and the output neurons. Now, if you have a certain condition where both the neurons are on, that means if two interconnected neurons are on simultaneously, then what happens? Then the weights associated with these neurons can be increased by the modification made in their synaptic cap. That means automatically the connecting links between these two interconnected neurons must have must associated with a kind of weight vector, and that weight vector is going to be updated, and you can see there is an increment, proportional increment by the modification or by the weight updation. So what is that weight updation rule? Weight updation rule is, that means now at this particular stage, you have some weight vector, you have some value of this weight vector. This weight vector can be treated as old weight vector, and automatically you will have a kind of, the product of this xi and y. That means now you have some, value of the input neuron, as well as you have some value of the output neurons. Now, if you compute that old weight vector, and if you add this particular old weight vector to this product of this input neuron and output neuron, for all the neurons you have, then automatically you will get, for that particular step, you will get a modified weight. That means a new weight vector. So this is the weight updation rule that is going to be followed in case of Hebbian network. And in that particular network, you can see that this particular network is more suitable uh, for bipolar data. I mean, than any kind of binary data. Now, this is somehow the Hebbian learning in a particular neural network is going to take place. That means every, in every such case, in every such, layers you can see, there is a kind of first neuron, and you can have a particular connection with the immediate next neuron, right? Here you cannot expect any such connecting links you can see. That means from first neuron to third layer neuron. So every time you can have a connection link with the previous layer to the immediate next layer, and again to the next immediate layer, and to the next immediate layer, and so on. And finally, you will have a kind of, output signal, or output value, output matrix, whatever you can say. So these are the, output side of this particular neural network when you utilize a Hebbian learning. Now what happens that if that particular, that means if that particular two neurons are, simultaneously on, that means whenever you have a kind of node I, and you have a particular next immediate node J, and two neurons are simultaneously, on, then what you will happen, you will go to, compute some Wij, that is the weight matrix. So automatically that weight vector or weight matrix is going to be followed, in the next phase also as well. But whenever you are getting, a kind of situation that here the J is also, highlighted, and another node is going to be highlighted, then what happens that then those weight vectors of two such neurons are going to be updated. That means that Wij is going to be updated with a new one which replaces the old one, and automatically whatever be the, input for this I node, and whatever be the output we are going to expect here after this particular, node. So this is what Hebbian network is all about. Now coming to the very one such rule which is called delta rule, or least mean squared rule, or Wiedrohoff rule. What I have told you in the first slide, where we have mentioned all the important neural network, there I have already mentioned that we have such one neural network which is called Adaline Network, right? And that Adaline Network is basically following this delta rule, or least mean squared rule, or Wiedrohoff rule, since the inventor, the designer or of this particular network is Wiedrohoff. Now what happens? This rule, is going to minimize mean squared error. Mean squared error means there must be some kind of now error between the actual value and the desired value. That means the actual output, what we obtain from the neuron, and the target value or the desired value where we want to reach. So in that particular case, this particular rule is used to train Adaline. So what is in one more question, sometimes you may expect this kind of question, that what is the full form of Adaline. So you need to learn that this Adaline is nothing but adaptive linear neuron. Why does it call so? That means adaptive linear neuron. What does this mean? This means that why it is called a linear neuron, because it has a single linear unit. So what does this mean? The single linear unit means an unit, obviously this is one unit, where, I mean, just like every neural network, does have that kind of unit. So that is one unit with linear activation function. So in that case, you can say, or you can understand, this Adaline is going to have a linear activation function, and we know that this activation function, always represents the, or indicates, you can say, indicates the input output relationship between, of a particular neural network. So what that means, if this is a linear activation function, so automatically Adaline also, offers some linear input output relationship, and it has only one output unit. That is why it is called single linear unit. That is the only, it has only one output unit, which is a very much different to what we have learned so far. The various types of neural network, it is having only one output unit. Now, in case of inputs and outputs, since all the relationship that input neurons and output neurons are holding, which is a linear one, so basically what happens that all the weights between these inputs and outputs are adjustable. Obviously, there is a rule which we are talking about. So automatically, when there is a rule, automatically there is some kind of updation rule, weight updation rule. That means weights has to be adjusted. Now what happens that in case of any neural network, now we know that we can expect a bias input as well, where we are saying that the bias value is a kind of 1 everywhere. So here also, in case of Adaline also, bias also acts like an adjustable weight, whose connection is from a particular unit. Obviously, there is bias is treated as a unit 1, a particular separate unit, and here the activation is always 1 for this particular bias unit. So if that is the case, then how can we visualize this kind of rule? If we go further, and if we have this kind of slide, then we can understand how this delta rule is going to be performed in case of Adaline neural network. Now what happens that in case of this kind of rule, so whenever we are having this kind of delta rule, you can see that here we are talking about the error between the net output, between the actual output which we obtain from the neural net, and automatically the target output or the desired output, between which we are going to apply the delta rule on the weights associated with the neuron, so that this error can be minimized. Now in that particular case, this delta rule is treated as it is a specialized version of backpropagation's learning algorithm. Backpropagation, what we have mentioned in the second slide, that here, in case of backpropagation, we can expect a particular, a feedback connection where the errors can be propagated from the output layer to the hidden layer, right? So here also automatically we can have to minimize the error, which is the least mean square error. So automatically what we need to do is we need to automatically, have some kind of, this kind of feedback techniques, so that we can measure every time the difference between the target output and the actual output, and we can apply some particular, formula or computational technique. So what can be that computational techniques? So computational techniques is nothing but whenever we have this kind of, calculated output, which is the real output or actual output, which is coming from the neural network. And if we have a sample output data, that means the desired output or the target target data, then we can use this particular modification to the weights. So in that particular case, we can implement a form of gradient descent rule, You can see here we have term a particular a parameter which is called beta. This beta is nothing but the error. That means the error between the calculated output and the sample output. And this beta is nothing but t minus o. We can formulate this beta as well as, like this. That means the difference between target and the output, which is the calculated output, nothing but calculated output. And we can have a particular, learning. This is a learning rule. So we can have obviously the learning rate, mu, which we have already, studied in the perceptron, that we can expect an alpha or mu or, a as an learning rate. That means the rate at which this weights are going to be updated. So here also we have some learning rate, which is defined as mu. We have some error value, which is now obtained from this calculated output and the sample output, and we have input value. That means for a particular step, for a particular input neurons, automatically we can obtain a certain calculated output, and we have found that there is a certain error between that calculated output and the sample output. So we are going to take that particular input value. Now, by multiplying all these three parameters, now we are getting, delta W. That means the differential value of this W. That means a very small, variation in weight, which we can add with the weight what we have in this particular stage. And in this manner, we can obtain the new weight, which is going to be, utilized or applied, for the rest of the, process, or for the rest of the training algorithm. Now collect this old weight and with the new modification weight, and automatically this network, changes its weight by this weight adaptation formula or weight adaptation rule. So this is how delta rule works. Now obviously we know that this particular, delta rule is going to be, used or utilized in case of, Adaline network. So what is that? Now you can see that this is what Adaline network is all about. So in that particular case, this Adaline network, if you can see that this is something which we can expect that we have one summation, one summation, because we have more than one inputs in this particular, for this particular network. Why? Because we have some, standard inputs, which is starting from, let's say, x1 to xm, and automatically, or it is a u1 to um here for this particular figure. We have one bias input as well, and bias, you can see that it is every time this bias input is taking as the activation function of 1. That is why straight away 1 is being written here. And now what happens that all those connecting, links, that means all those connecting links or synaptic links, those are associated with the weights itself. So those are also W1 to Wm, and for this weight, we know that this is a bias, so automatically this is the value of 1. And what we have here is W0, this is a 1. Now what happens is all these are coming into the summation or the aggregator. So what happens that this is what, Adaline output Y. But this is some kind of, net input, which is now coming to the, the network, where you can expect one activation function. So here, by utilizing this activation function, now you can expect the final output value. But whenever you are getting, applied this Adaline output into your activation function, which is the function for the given problem, that means you have designed some kind of activation function for your given problem, you are going to apply this Adaline output into that particular function. Now what happens that whenever you have a certain output for certain input vector, suppose you are getting, this particular output is again, getting into the comparator. So what you can see is, suppose you are getting one error E. So this is one error, that means, which means that there is some error between what we are getting from the Adaline and what we have as our desired output. So automatically there is a difference between this Y and D, and for this particular error, we need now one weight adjustment techniques, which is nothing but based on the delta rule or Wittroff rule, so that we can change all the weights. And that weight updation rule is already I have covered in the previous slide. Now what happens that in this particular network, as you can see, this is a single unit neuron, because it is producing only one output. So basically only one output neuron must be there. It receives inputs from several units, what we have already seen here, and also from bias, what I have just told. And inputs here also are either +1 or -1, that means either excitatory or inhibitory. And weights are also, excitatory or inhibitory, that means +1, that means greater than 0, or less than 0, that means the -1. And in that particular Adaline, I mean, to solve any kind of neural network problem with this Adaline network, what we need to do is, we need to, initially assign some random weights, what we have done for the Perceptron network as well. And every time we are going to compare actual output with the target or the desired one. And based on the, output, that means based on the error, if we are getting any kind of, error, that means based on the compared value between this actual output and the target output, delta rules are applied, which basically modifies the weight or adjusts the weight. So here, if you cover now the perceptron, if you now cover the delta rule, that means the Adaline network, one very popular question are usually coming in the semester, in the Viva, that is, what is now the difference, or how can you differ the perceptron rule from delta rule, or vice versa? So what we have here is, whatever we have come across by learning all these two rules, we have obtained that this perceptron rule is a thresholded output, whereas in case of delta rule, we cannot find any kind of this threshold value, right? So this is one, one difference you can see. Another thing is, this perceptron rule originates from Hebbian rule, Hebbian perception or Hebbian assumption, you can see. But here, on the contrary, this delta rule, originates from gradient descent method. That means automatically there must be some difference between this Hebbian rule and the gradient descent method. So in the next class, on the next day, we would start from this gradient descent method first of all, because we have already mentioned in this perceptron slide as well, perceptron topic, that we have now gathered a little bit idea about the gradient descent method. But obviously, if it comes as a short note in the semester exam, then we would have to know, a little bit more about the process, how this particular method works, and that will be covered in the next class. Now what happens is, the third, difference between this perceptron rule and the delta rule is that it converge, or it can stop after a finite number of iterations. That means, you can remember that once I have mentioned that in case of, this kind of neural network procedure, you can mention the number of iterations at the beginning. So automatically, if that finite number of iterations has been arrived, so automatically this perceptron rule, it can converge, or it will stop, that particular on this hypothesis. And that, but obviously there must be such case that after completing that particular finite number of iterations, that hypothesis can perfectly classify the training data. Otherwise, there is no use, And obviously, providing the training data are linearly separable. But in case of delta rule, what happens that if this particular algorithm, can run forever, can continue forever, right? Because it converges only, asymptotically towards the error minimum, because its main aim is to minimize the error. Its main aim is not on that particular, point that we want to, converge into any global or any local optima. So basically what happens that possibly it requires unbounded time. That means it can continue forever, but obviously it converges regardless of whether the training data are linearly separable or not. Now what happens, so that is why the fourth and the last, difference I have mentioned here according to, between this perceptron and delta rule, it exclusively, this perceptron rule exclusively performs on linearly separable data. As you can remember that we have applied this perceptron rule on the on the OR function, right? On the OR function, AND function, NOT function. But in case of XOR function, we can have this multi-layer feed-forward neural network. So that is one such very important point, very fundamental point about this perceptron rule, that it performs only on linear separable data, whereas delta rule, can also work in linearly non-separable data. So these are all the differences what we have in case of perceptron rule and delta rule. And this is all about today's class. So thank you.